Hey Bulldogs, we are continuing our study of chapter 4.5, and in the previous lesson you guys learned about curve sketching, and we did an example of rational functions. We did example number 3. I just wanted to post one more video in case you wanted to see another example. So the other example we're going to look at is the one on the bottom, f of x equals x over x squared minus 4. And I'm just going to do this on a separate piece of paper here. So this is chapter 4.5. And this is the function f of x equals x over x squared minus 4. So when you're doing your homework, you're not going to see, it beautifully laid out like this for you. But when they ask you to sketch a rational function in your homework, you want to follow these same steps. If you're an IB student, an IB question will walk you through all of the parts that they want you to find usually. All right, so the first thing we're going to do is we are going to find the domain. And so our domain comes from our denominator. We know that if we have any kind of restriction in the domain, we're looking for radicals, we're looking for logs, we're looking for denominators, and I sure do have a denominator here. And so I am going to set my denominator equal to 0. You can factor or you can move your 4 over. And when you take the square root of both sides, we see that x cannot be plus or minus 2. There's always the option that it could be a removable discontinuity, but I'm not seeing anything canceling out on top and bottom. So there are no holes. These are actually vertical asymptotes. So for my domain, our domain would be negative infinity to negative 2, negative 2 to 2, and 2 to infinity. Okay, the next thing, and again, I'm just following these steps right here. The next thing we're going to find are the x-intercepts and the y-intercepts. All right, for our x-intercepts, we know that we are going to be substituting 0 in for y. For our y-intercepts, we're going to be substituting 0 in for x. So, to substitute 0 in for y, I'm going to have 0 equals x over x squared minus 4. We know that when you have a fraction's only equal to 0 when the numerator is 0. So you can just set that numerator equal to 0. So we get the x-intercept of 0, 0. If you didn't realize that, you could put a 1 underneath there and cross multiply and you get the same result. For my y-intercept, I'm plugging 0 in for x. So f of 0 equals 0 over 0 squared minus 4, which is 0. And obviously that makes sense. If we had the x-intercept at the origin, that would also represent the y-intercept. Remember, you can have multiple x-intercepts. We can only have one y-intercept because we're working with a function here. All right, the next option is symmetry, and I think most of you aren't using symmetry, so I'm going to bypass that. And next up, we're going to look for any asymptotes. So we want to identify horizontal asymptotes and vertical asymptotes. So for your horizontal asymptote, we're going to compare the degree in the numerator and denominator. The denominator has a greater degree because that's an x squared, which means that our horizontal asymptote is at 0. Remember, when the numerator has a greater degree, there isn't a horizontal asymptote. When they are the same, you grab the quotient of their coefficients. And then for my vertical asymptotes, well, we know that comes from the denominator. We've already found those vertical asymptotes. Here they are. So x equals plus or minus 2. All right, next up, now we're getting into, let me cut back over here, we're getting into f prime of x and f double prime of x. So we're going to do our first derivative test to identify maxes and mins, and then increasing, decreasing tests to identify those intervals, and then we'll continue on to find concavity. So for part E, we're going to find f prime of x, which means I am going to be using my quotient rule. So low is x squared minus 4, d high, derivative of x is 1, minus high is x, d low is 2x, and that is all over the denominator squared. Okay, so we're going to clean this up. Now, normally I'd look to see if I could factor anything out. There's nothing to factor out, so I'm just going to distribute and clean up a little bit. So x squared minus 4 minus 2x squared. So that would be negative 4 minus x squared. And now, sorry about that. And now we're going to set this, we're looking for where the derivative is 0 and where the derivative doesn't exist. Well, the derivative is 0 when the numerator is 0. The derivative doesn't exist when the denominator is 0. And I already know about the denominator. We know that's our vertical asymptotes. For the numerator, I'm going to slide my 4 over, and we actually, when you divide by a negative, you actually get an imaginary number. So we don't have any critical values where the derivative is equal to 0. So the only critical values we have are the vertical asymptotes at plus or minus 2. So let's go ahead and draw a sign diagram, negative 2 to 2. We are substituting those into f prime. So let's substitute negative 3 in. So negative 4 minus a negative 3 squared would be 9. Negative 4 minus 9 is negative. And negative 3 squared is 9 minus 4 squared. Anything squared on the bottom is always going to be positive. So a negative over positive is a negative. In the middle, if I substitute a 0 in, negative 4 minus 0, that's negative, and anything on the bottom is going to be positive here. So that's going to be negative, and then substitute a 3 in. We get a negative on top, we get a positive on the bottom, so that's also negative. So our increasing intervals, well, there are none. Our decreasing intervals are everywhere but at negative 2 and 2. So negative infinity to negative 2, negative 2 to 2, 2 to infinity. So this is actually decreasing everywhere in its domain. We don't have any local mins or maxes because there are no sign changes here. All right, we are ready for the second derivative, and that is our concavity test. So we're going to be finding f double prime of x. This would be step f here. Whoops. And I know that I want to find the derivative of f prime, so I'm going to go to my most cleaned up version of f prime to find my derivative here. And I'm using my quotient rule again. So I would have low, which is x squared minus 4 squared. D high is negative 2x minus high, which is negative 4 minus x squared. D low. So my 2 comes to the front. My x squared minus 4 carries down. Power drops down to a 1. Don't forget your chain rule. So times x squared minus, times the derivative of x squared minus 4, which is 2x. And this is all over x squared minus 4 squared, quantity squared. Okay, so I'm going to clean this up. And to clean that up, you certainly could distribute that out. I do not want to distribute that out. I'm just going to go dive right into factoring here. And so what I'm seeing I can factor out. Now, if you like to clean it up first, you can. You know, a lot of students prefer to do that. I'll go ahead and show that. So I have this negative 2x in the front times x squared minus 4 squared. Here I have 2 times 2x, which is going to give me minus 4x in the front, times negative 4 minus x squared times x squared minus 4. I mean, it didn't really clean up that much. On the bottom, we have a power of 4. So now is when I want to factor, because I know I'm going to need to set my numerator equal to 0. So look at your two big terms. What do they both have in common? Well, they both have a negative 2x that I can factor out. They also both have an x squared minus 4 raised to the 1 power. So when I divide, my negative 2x cancels. X squared minus 4 squared divided by x squared minus 4 to the 1 leaves me with x squared minus 4 to the 1. Negative 4x divided by negative 2x is positive 2. This negative 4 minus x squared carries down, and my x squared minus 4 cancels out. And that's all over x squared minus 4 to the 4th power. Let's keep going. All right, so we've got negative 2x. Now, I am also seeing, this isn't a factored form now. I do have some cleaning up in here to do, but I'm also noticing that this factor on the front cancels with the one on the bottom. This happens very often. So, one of those cancels with one of those. And so that leaves me with negative 2x. And in here, I'm going to go ahead and distribute. So x squared minus 4 minus 8 minus 2x squared all over x squared minus 4 quantity cubed, and we'll go one more step. So I have x squared minus 2x squared, which is negative x squared minus 12. Okay, now I'm ready to set this thing equal to 0, which really means I need to set the numerator equal to 0. And if you want, you can set each of those factors equal to 0. So if you set the numerator equal to 0, don't we just wind up setting them separately equal to 0 anyways? So if you want to skip that step and just go straight to the step where you set each individual factor equal to 0, that's fine. And then we also know we've got to set the denominator equal to 0 to look for where my derivative doesn't exist, but we recognize that. That's our two vertical asymptotes, plus or minus 2. You've heard me say it before, but once you see a vertical asymptote, every subsequent derivative will have the same vertical asymptotes. All right, so we've got x equals 0 as a critical number. When I slide my 12 over, divide by a negative, we are getting an imaginary number. So we get nothing from this one, and I have plus or minus 2. So we've got 0, we've got negative 2, we've got positive 2. I already know that these are vertical asymptotes, but let's see what's going on here. So we're going to substitute these numbers into my f double prime. So negative 3. So negative 2 times negative 3 is a positive. Any number squared times a negative is a negative. Minus a 12 is going to be a negative all the time. I like to circle it when it's never going to change behavior. Negative 3 squared is 9. Minus 4 is positive. Cubed is positive. So we have a positive times a negative over a positive, which is a negative. Substitute negative 1 in. Negative 2 times negative 1 is positive. Negative 1 squared is negative minus 12, that's always negative. Negative 1 squared is 1, minus 4 is negative 3, cubed is negative. So we actually have a positive times a negative over a negative, that's going to be a positive. Let's plug 1 in. Negative 2 times 1 is going to be negative. This will be negative. 1 squared minus 4 is negative 3, cubed is negative. So 3 negatives make a negative. And then greater than 2 like 3. Negative 2 times 3 is negative. Negative 3 squared, that's negative. 3 squared is 9 minus 4 cubed is going to be a positive. So a negative times a negative over a positive is a positive. So for my concavity, this is going to be concave up from negative 2 to 0 and from 2 to infinity. This is going to be concave down from negative infinity to negative 2, from 0 to 2. Inflection points. Now, if you have a sign change, you know you have a concavity change, which is an inflection point. However, negative 2 and 2 are vertical asymptotes. So you can't have an inflection point on a vertical asymptote. So my only inflection point is going to be at 0. And I do want to find my coordinates. And that has to come from my original function. So remember, my original function was x over x squared minus 4. So I'm going to substitute 0 in here, which we've actually already done. That was our y-intercept. So we get 0. So we have an inflection point at that x and y-intercept. Okay, we are ready to sketch this thing. So who knew I'd need 3 pieces of paper for this problem? Goodness. All right, so what we're going to do is we're going to take all of the information that we have already. So I'm going to draw my sketch, and I'm going to start plotting my points. So remember, I'm starting in the beginning. We have x and y intercept at 0, 0. Here it is. We have a horizontal asymptote at 0 and vertical asymptotes at 2 and negative 2. So here's 2, here's negative 2. We have vertical asymptotes here. And then we have a horizontal asymptote at 0. Okay, let's keep going. So now I know that my entire function is decreasing everywhere, and there were no local maxes and local mins. Now that already starts to give me a really good idea of what this is going to look like. If this needs to be decreasing everywhere, decreasing here, 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 and here, On the left side of this vertical asymptote, in order for it to be decreasing, it can't possibly be a branch up above. It only can be down here. Now I'm just drawing this with a pencil because we might hear about, some concavity changes, something strange like that. And if it's decreasing in this middle section, there's no way it could come from down here and go up because that would be increasing. So my only option is it's coming from up here, and I know it's got to pass through that point, and I know it's got to continue to head down because it's decreasing. And then for this last interval, it can't possibly be a branch on the bottom right because it needs to be decreasing. So I think it's going to look like this. This is my guess, and I haven't even looked at the concavity yet. So our last thing is our concavity. So remember, this thing was concave up from -2 to 0. I'm going to make my little concavity continuum down here. And then also from 2 out to infinity. It is concave down from -infinity to 2, and then from 0 to 2. And then we had an inflection point at 0, 0 right here. All right, so let's check our concavity. So concave down, but it's decreasing. Yep, what I had here in pencil is looking pretty good. That is a decreasing function, and it is absolutely concave down. For this next section, it's decreasing, but it needs to be concave up. So make sure it has that curvature like an upward-facing parabola. And then at this inflection point, it switches, so the curvature becomes concave down. And then in this last section, this is concave up, so what I had there is looking good, and it's decreasing. So we're able to make kind of a good estimate just by looking at the decreasing characteristics of this graph. Okay, so that was the last example in your notes for this chapter. I hope that you found this second example helpful, and I wish you guys all the best of luck. Thank you so much for listening.